केबल स्टिकर है हाँ सर వినబడ ఎలా చూడండి వినబడం
Participants are very, very important to us, right? Thank you so much. Today's significance, Sir C. Raman's birthday. Just we will have a small glimpse.
India observes February 28th as the National Science Day. On this day, 1928, celebrated Indian scientist Sir C. V. Raman discovered a phenomenon scattering of photons, which was later known as the Raman effect, after his name. After 2 years, in 1930, he got Nobel Prize for his discovery, and this was the first Nobel Prize for India in the field of science. To mark this discovery, National Science Day is celebrated in India on this day each year. Raman effect is the change in wavelength of light that occurs when a light beam is reflected by molecules. When a beam of light traverses a dust, we must current sample of a chemical compound. A small fraction of the light emerges in directions other than that of great incoming beam. Most of this scattered light is of the unchanged wavelength. This is the Raman effect. The objectives of the National Science Day are to widely spread a message about the importance of science used in the daily lives of people, to display all the activities, efforts and achievements in the field of science for human welfare, and to discuss all the issues and implement new technologies for the development of science. Theme of the year 2017 is Science and Technology for Specially Abled Persons. The first National Science Day was celebrated in the year 1987 on 28th of February. Now, News, New Delhi.
మధ్యలో ఎలా చూస్తున్నాను ఓకే
Good morning, respected Principal Sir Dr. K. Muralikrishna garu, Honored Chief Guest K. Nageshwar Rao garu, Department of Atomic Energy, Executive Engineer, NFC, Hyderabad. Welcome, sir. I welcome all my teachers, my dear friends. Today we gathered here to celebrate National Science Day 2026 Innova, a day that reminds us the power of curiosity, discovery and innovations. It is a day that encourages your minds to question, explore and create. The theme of National Science Day 2026 is Women in Science, Catalyzing Viksit Bharat. This theme celebrates the vital role that women scientists play in building a developed and progressive India. It highlights the need for greater participation of women and girls in science, technology, engineering and mathematics. National Science Day is celebrated every year on 28th February to commemorate the discovery of Raman effect by the great Indian physicist C.V. Raman, for which he is awarded Nobel Prize in Physics in 1930. His groundbreaking discovery not only brought global recognition to India but also proved that dedication, observation and scientific thinking can change the world. On this special occasion, I feel privileged to extend a warm and heartfelt welcome to our respected principal, whose constant encouragement inspired us to aim higher. I also extend a gracious welcome to our esteemed chief guest, whose presence today adds great honor and value to this celebration. A sincere welcome to all our dedicated faculty who nurture scientific temper in us, and my dear fellow students who are future innovators, researchers and problem solvers of tomorrow. The significance of National Science Day lies not only in remembering an historical discovery, but also understanding the role of science in our daily lives. From the smartphones in our hands to life-saving medicines, from space missions to sustainable energy solutions, science shapes our present and builds our future. It teaches us to think logically, act responsibly, and solve problems creatively. Dear friends, India has always been a land of brilliant scientists and innovators. Following the footsteps of pioneers like Dr. C.V. Raman, we took a dream big and contribute to the progress of our nation. On this National Science Day, let us pledge to develop a scientific temper, to respect evidence and truth, and to use science for betterment of humanity. With these words, I once again welcome everyone to these wonderful celebrations. Thank you and have a great National Science Day 2026. To commence this auspicious occasion, let us now invite respected Principal Sir to the dais. Welcome, sir. Now I would like to request our Honorable Chief Guest K. Nageshwar Rao garu to the dais. I request Veena ma'am to present the bouquet.
సిగ్గుపడకు
I request Bharti ma'am from the Physics Department to present the bouquet. Lighting the lamp signifies initiating an event with divine blessings, knowledge, and prosperity, removing the darkness of blind enlightenment. Let's begin this event with traditional that signify knowledge, wisdom, and prosperity. I request the dignitaries to please join with the light lamp and also all faculty members to join for the light lamp.
రండి బాగా భూమేశ్వర్ సార్
I request the faculty members please join in the light lamping ceremony.
మేడం
To commence this auspicious occasion, let us call our respected principal sir, Dr. K. Krishna Garu, to speak few words about National Science Day. Welcome, sir.
Good morning to all. Respected C.K. Nageswara, retired scientific officer, Nuclear Field Complex, Hyderabad. K. Madhavi, HOD of Department of Physics. Bharti Devi, Senior Faculty in Physics. Other my fellow faculty members and dear students. Today, we're all gathered here to celebrate National Science Day. Of course, every year on 28th February, observed as National Science Day to commemorate the remarkable discovery of the Raman effect by the great Indian scientist C.V. Raman. For his extraordinary work, as Madam said, in 1930, he got Nobel Prize. That's making our nation proud on the global stage of scientific excellence. National Science Day means it's not a simply celebration. The curiosity, interest, towards the subject, making the hidden talent is outside the world. Innovation, continuous and work together our science. Nowadays, of course, every time, the basic science, it is the foundation of our civilization. Actually, our India has made remarkable contribution to science and technology. Institutions like ISRO have demonstrated our technological strength through successful space missions such as Chandrayaan 3 and Aditya L1. Showcasing India's capability in space exploration. Our scientists, engineers, researchers continue to push boundaries in artificial intelligence, biotechnology, renewable energy, and healthcare, etc. Actually, the science is not confined to laboratories. It begins with a question: why and how? These two are very, very important things. Every student is a scientist who dares to question, experiment, and innovative ideas. He is a scientist in the making. So therefore, the students, whenever you learn something, the important thing is why and how they are working, where they are going to apply. These things we have to observe. The curiosity, the innovative ideas definitely will make you as perfect in science. So every time, as I said number of times, we have to update ourselves. Either computer science, or science and technology, or in other areas. Day to day, we have to update ourselves. If you want to settle in your life the perfect manner, the things are very, very important things are, you should update. As for the market requirements, we have to learn new emerging courses, new emerging technologies. These things always we have to learn. Otherwise, there is no life. Otherwise, always we will be lying only. Whenever we adopted the emerging technologies to your education, then definitely you can reach high in health. No doubt about it. Right? And also, yesterday, on the part of National Science Day, so of course every year in our lives we are celebrating National Science Day and other events also. You all know that we have very good infrastructure, good labs, good library, and other things. The important thing is we have to utilize all such things in a proper way. So on this occasion, let us remember that science is a tool for national development and global progress. It plays a crucial role in achieving self-reliance, strengthening our economy, and addressing challenges like climate change, health issues, and sustainable development. Dear students, I encourage you to cultivate curiosity, embrace experimentation, and never bother about like to fear failure. Great discoveries often emerge from persistent efforts and courageous thinking. Let us try to use science not only for advancement but also for the betterment of humanity. As we celebrate National Science Day, Let us pledge to promote scientific thinking, support research and innovation, and contribute meaningfully to the progress of our nation. So, dear students, once again, my congratulations to all the participants in our recent events, as well as, of course, in very soon, that means in the month of April, like your examinations also are going to schedule main theory examination. But one thing is always you remember that examination only to get certificate. But the reality is different. The reality is different. Those who are having certificates with 9.9 CGPA may not settle in the life. Whereas those who are having or average students may settle in life immediately. The difference is the interest. Showing your interest towards the subject, otherwise to the market. That means, as for the market needs, we have to convert yourself. You should fulfill the market requirements. That is important. That is science and commerce or any other area. But as for the market requirements, if you can transform, automatically you will be settled in your life 100%. I wish you all the best. Thank you. Thank you.
Thank you so much, sir, for your valuable words. Now, I am very privileged to give the profile of honorable guest K. Nageshwar Rao Garu, Department of Atomic Energy, Executive Engineer, NFC, Hyderabad. Sir was born on 29 December 1965. Sir has completed his degree in Chemical Technology from Loyola Academy, affiliated to Osmania University. Sir has done Diploma in Computer Applications, certified with C, C++, VC++, Java, Professional. Sir worked as Junior Project Engineer in Bucket Hiram Limited during 1987 to 89. He developed phenolic foam production process for the first time in the world. Please applause with your huge clap. And executed its manufacturing facility. Sir worked as process engineer in Southern Formats Private Limited during 1989 to 90. Sir worked as scientific officer with Nuclear Fuel Complex during 1990 to 2025. He contributed as process and design improvement officer in uranium oxide plant where we have visited recently on February 17th. He has worked as he is presently member in Indian Nuclear Society and Indian Institute of Chemical Engineers. He has presented a couple of papers at ChemCon related to key improvements in nuclear fuel manufacturing at NFC Hyderabad. I am very much privileged sir, to have you here. Now I request you to please carry on with your seminar, sir. I welcome you, sir.
Good morning, all. Thank you, madam. I am. Let me express my feeling. I am happy to see you all here, addressing students for the. I think this is the second time in my life. Always have been talking to at a different level, in industry and engineers. So I'm happy to speak to you all. And I thank Dr. Murali Krishna principal, who have honored me to and invited me to speak a few words here uh, with respect to science and the future for your endeavors. Okay. So, your principal sir's speech was very enlightening to you all, I believe. So, the way sir has told about Dr. C. Raman, you should know one thing that those days when 1920s and 30s, we were hardly having even a transport, and there were no laboratories as you have today. But still, there was no even hardly any books also. But they used to put a lot of thought process in their mind with the limited knowledge they had, and they used to get innovative ideas and to realize them, to check whether these ideas are correct or not. They used to write letters to elsewhere scientists around the world. So those days were very tough, actually, very tough. So in such cases also, such situations, those people have excelled. They have innovated basic sciences, many new ideas of science which are helpful to us today. So today, when we compare ourselves with those days, we have all infrastructure. Like sir told that you have very good labs, you have good auditorium here, you have good infrastructure of the college, you have good lecturers to coach you, you have good libraries, and over and all above you have your mobile and internet, computer. You can explore the science and technology available in the world. Sky's the limit for it. Do you agree? So we should feel proud that we are existing in current generation and in the this 21st generation, and we are having all these facilities. As sir said, very importantly, he has mentioned that we all should you all should innovate, think towards some constructive ideas to develop something, innovate something, or improve. If not innovate and all, something is there which you can improve always. So that is what I could say. It was a very good speech, sir. Well, coming to my presentation today, I have, as I've been introduced, I have worked for nuclear fuel complex till recent past, from which company I have retired also, so superannuated. So I feel very proud also, not just happy, proud, because I have got into an organization where we have contributed to the country a lot. Okay, we have contributed to the country a lot. In the year, I should say in the year 1947, which we have got an independence and all, post that, 50s, 60s also, we were struggling. You all must have read your social books. I just try to recollect. Even I have read like that. We were not having an industry where we could even manufacture anything. So those were the days then. From there, from that kind of situation, we have come to a stage where we have IITs in India. Major industries are existing in India today, and a lot of R&D is going on. So one of the field which has excelled during this period is nuclear power. So that is what is I wanted to take you into a field where you are not very, you may not be very conversant with it. It is altogether a different field. Not much is there in the books and all. okay, we are very proud. I am very proud, and all this our organization, which is called as Department of Atomic Energy, which has been founded by then Dr. Umi Baba and then Prime Minister Mr. Jawaharlal Nehru. They have seeded this organization in India, and it has contributed to country a lot. Today, I am proud to say that India is ranked at say around the third in the world of this nuclear power. Out of 195 countries, we are ranking at third place with respect to nuclear science and technology. So yes, there is a lot of scope for improvement, discovery, innovation, and taking our country forward. And you all are very young at college level, so which you have to stick to your books and then contribute much more to the country. You have a chance, people like us, we have missed the bus, missed in the sense, whatever we could do, we have done. In future, it is your part to play. Okay, and that's what I would like to say. Now coming to this nuclear power and all. So most of you, as I said, you are all from BSc graduates. So maybe in the second and third year most probably. So you must have heard about this, study about modern physics and all. You have studied in the intermediate level also. Alright? So it is nuclear science and technology has started, or it is derived from modern physics. It is all about your atomic physics and later it is quantum physics. So I would straight away go into this nuclear power and all. Now why nuclear power and what is its importance is very important for us. See, when we if we really go back prior to 1900s, okay, all countries, not just India, all countries were having only one agenda. That agenda was to survive. To survive, food is required, okay, and for food, agriculture and animal farming. These two are very important. Now, after 1900s, slowly the trend has changed. That industrialization was to happen. Why? Because the discovery of power, availability of electricity to the common people or citizens who are made available through various projects like idle projects were the first facilities in all over the world, all countries. So gradually what happened is power, then it is lighting, then it is some motors, it is some industry and all like that. So but in the meantime what happened is the power, we have many sources like we used to get first power discovered is from hydrogen, right? Thereafter it is batteries and all. Batteries will not give much power, it is only for very miniature requirements. So DC current was first discovered. Later Tesla has discovered the alternating currents. Thereafter slowly many transformers and all have come. So as we are enhancing towards industrialization, the key factor which was required is a requirement of power. So for any industry, see we are assembled here in this hall. So without power, without AC, without this all media and all, for all these things power is required. Power is electricity. So like that, as the population is increasing, industrialization is increasing, technology is increasing or enhancing, so power has become a key parameter or factor for growth of a country. So in our country, somewhere in the year around 1950 and all, government has taken action that along with the industrialization, we should have a energy commission also. So energy commission generally deals with power security, electricity security for the entire country. So then it was only hydel, slowly the thermal plants have come. But the industrialization in India has taken a very fast pace. Fortunately, people like Tata and all, they have started that moment in India, and thereafter many other industries have started. So what happened is there was a decline in the power requirement. So all other alternatives were being proposed. One, apart from hydro, it is we all know it is wind power is what they have thought of. It is very best alternative. Thereafter, it is solar. But in any case, when you compare with this hydel, solar, wind, so here what happens is hydel only when water is there, sufficient water is there, only then hydro power projects can run and generate power, right? We agree. Then if it is solar, only when sun is there, then you can get a consistent power supply. And when in case of wind also, only those areas where elevated areas where wind is good, from there we can generate some power. But all these will not have a consistent power supply. Consistent is continuous, whatever required, that much of power cannot be generated. And we cannot generate power and even store also. That is not possible. So then scientists were thinking what are the other alternatives. In the meantime, abroad people have in the 1930s and 40s, USA have come with this nuclear power. Okay, so thereafter India, Dr. Homi Baba also has proposed why not we have this nuclear power in India. So that's how atomic energy in India started. From there, we have we today this particular slide you can see power produced in 2025 is 1825 terawatt hours. Okay, and what we produced, what we consumed is only 1704.
Hello, Moto.
Then government and our chairman of atomic energy have taken a very important decision. You all must have, I don't know how many children must have seen or know that
Hello.
staff may be knowing, must have read about this. No. So there was an agreement called 123. So this 123 agreement we had with USA. Okay. So this 123 agreement is what makes India self-sufficient to get nuclear fuel from abroad. So to make the nuclear reactor run, anybody? Uranium is a basic material. Uranium is the atom from which we get nuclear power. So we had very less, very weaker deposits of uranium in our country. They are mainly located in Jalura, Bihar. So there we have started in 1950s only. We have excavated, then extracted uranium from the mother earth. But the percentage was very low. It is somewhere around 0.02 to 0.03%. Can you imagine? 0.02, 0.03%? Very, very low. Nobody even value it. But from such low percentages, we have extracted the uranium to almost around 100%. So that's a big industry, big process. So, but as I said, the quantities are so low in India. Then to make India self-sufficient, self-reliant with respect to energy, we need to have this uranium. So that's how America, then Bush, and Indian Prime Minister Manmohan Singh and our Chairman Mr. Anil Kapoor, Dr. Anil Kapoor, they have made a treaty with USA. This has changed the India's energy crisis and security. Today, that is the reason why we are able to produce that much of power today. So we are self-sufficient today, and this indicates a rapid or a scope to development. Many more industries can come. Okay, we have surplus power, so we can establish more industries. That's the reason why we are running around the world for investments into India. This is the basic thing. People may not be knowing, so I just thought let me bring it to you. So, okay, that is the slide. Okay, now if we see, we are here somewhere, I think 1, 2, 3, 4, 5, 6, 7, 8, ninth place. We are able to produce, this is 2024, which has given is 2025 there, in the earlier side. So we are able to produce around 50 terawatt hours in 2024. So 2025 official figures have not been announced. It is around 55. So still we are lagging. We are not even 10% of what USA or China are generating. So we have a big task in as a responsible citizen. We have to contribute a lot to the country for our development. So now, what is that? Is about nuclear power. See here, this is all. It is not generated by me. This is a slide which has been made by our Energy Commission, International Energy Commission, where we have declared that how many reactors we are going to see. These are the 24 reactors we have been operating up to 24. We have added another 2 reactors in 2025. So that's how we are now operating on 26 reactors. Here, can you see? Reactors operated at 24. Now this year it is 26. We have 106 reactors are under construction. Okay. Then 16 more are planned. Okay. Then 26 is for future up to 2070. That is the plan. So can we go to the next slide now? What does a nuclear reactor look like? So it is basically, it is like this. This is the main reactor area. Reactor in the sense there is a small reactor there. It looks very small. I'll give you a little detail of it. Then there is a steam generator. Then we have a turbine there. Okay. Then we have a cooling tower. So this is from a bird's eye view. You can identify the nuclear reactor like this. So nuclear reactor is a area where we put we use our fuel. That fuel you all understand now. We put fuel which is petrol in our bike and then make it to run. Okay. Like that, the reactor runs with a fuel which is mainly uranium. There are 3 isotopes of uranium. They are U-238, 35, and 34. Okay. So uranium-235 is a fissile atom. Fissile in the sense which can undergo fission of a nuclear atom, uranium atom. So when a nucleus of a fissile atom is broken, it generates a lot of energy. This you must have read in your intermediate also. So that contributes to around 200 MeV, mega electron volts. So that is the basic funda, okay, for which a nuclear reactor has existed. So this reactor which I am showing here, if I tell you how does it look like and what is the size, here it is very small. The reactor, the height of the reactor will be somewhere around 120 meters. Can you believe? 120 meter height from the bottom to the top of it. Okay, and the width will be minimum to around 70 meter dia to 120 meter dia. So that is the size of the reactor. Okay. Then we have steel generator there. In this reactor, the uranium particle, uranium which is put in the reactor undergoes fission when a neutron gets bombarded onto the uranium atom. So the nucleus splits and energy comes out. Okay, that is what is the main mechanism happens in the reactor. This heat is drawn out. So basically, uranium is in powder form, solid. Okay, it is a solid powder which is compressed to make a pellet. You all must have seen when you have come to uranium oxide plant, right? Have you seen, madam? Bundles and all? So they are made into pellets. Pellets are filled in tubes, and each tube is called a element, and several elements are made into a form of bundle. Okay, these bundles, several thousands of bundles go into the reactor. So that is called charging the reactor. So this uranium, when it gets an incident neutron, and when it splits the nucleus, it will release a lot of energy. That energy is drawn off by there is a pump there, and there is a closed loop of liquid. Okay, that is water. Okay, generally it is water. So this water takes away the heat and goes to that steam generator, where heat exchange happens with the other cycle of there is another loop of water. So in that the steam is generated. Steam at high pressure goes into the turbine. Turbines are made to rotate because of that high pressure steam. Okay. So when the turbine rotates, our generator is there which generates electrical power. That is connected to our. You can just go to the next slide now. So here this is how this is animated for you to understand. So this is the primary liquid. This is where control rods is written in the reactor. This cycle, this water releases heat to the cold water cycle, water line. So there the steam is generated, turbine is rotated, then from there the steam comes back to the a large pit where again water is cooled there. So cooled water again is taken into the steam generator. So why can anybody say? Why we are here we are heating and then cooling there. Okay, again we are getting the cooled water to again get heated. You understand why? Basic science. Okay. The idea is to draw the heat, right? Idea is to draw the heat from our reactor, right? There is one loop of hot water circulating in this loop. So from there heat is removed. So when the gradient, we call gradient, from if the temperature of that water, incoming water into the steam generator, as low is there, and it has to boil. So the difference in the temperature is very large. So we are able to draw more heat. Okay, that is the reason it is cooled. So then that's how the generator runs. Okay, from there it is connected. The power is connected to the grid. What you know? What is called a grid? Grid is something like any power generation plant. Even if you are generating from your house, if you have a solar panel over it, that also can be connected to the grid. So the power is going to the grid, where from grid people draw power to the respective record. So that is called the grid. So this is the basic function of a reactor. Now what exactly happens in the reactor we will try to know. Can we go to the next slide now? See here I have given how many types of reactors are there. Okay. Reactor you must have seen in your chemistry lab and all. You put some acid and then water, then these two react to form a salt and all, something like that. Okay, you must have done many other reactions also. Like that, here also a reactor in which this fission reaction happens. So PWR is called pressurized water reactor. This is one type of reactor. Okay. Then this particular reactor has a fuel called O2. E stands for enriched. 2 is uranium dioxide. Okay. So what is that? I have just told you about uranium exists in the form of 3 isotopes. Natural uranium exists in the form of 3. One is U-238. What is the 238? Can anybody tell? You can say, participate in the discussion. Huh? So U-238. Now 238 is the atomic mass of the atom. Okay. Isotopes are 3 isotopes. I said. The atomic number defines the atom, gives the name. So 92 is the uranium atomic number of the uranium atom. So 92, but atomic mass is 238, 235, and 234. So these 3 isotopes. So these 3 are the different atomic masses. So here U235 is enriched to 3.2% approximately. So enrichment is, as I said, uranium exists in the mother earth from where we extract the uranium. So this uranium which is purified will have all these 3 isotopes at some equilibrium. So this U235 in it is only 0.7%. If we make around say around 100 kg of uranium, pure uranium, in that only 0.7%, that is around 7 kg of U235 only will be there, which is useful to us. The remaining is all of no use. Understood? So what is that entire uranium is called? That is called okay, we can call it as a pure only. This is U235 is the fissile material, whereas U238 is fertile material. Okay, so this 0.7 is enriched. These days you must be reading news in the news, no? Iran. Have you heard about it? Iran has some enrichment facilities and all. USA and even United Nations are and IAEA, that is Indian International Atomic Energy Agency. These are an eye on them. What is it they are doing? So uranium, if it is enriched beyond certain percentage, say around 10% or beyond 20%, if it is enriched, it is a bomb, atomic bomb, nuclear bomb. So nobody can. It is difficult to keep it intact, not getting exploded. It is highly difficult. So enrichment is very difficult, very dangerous also. So here it is 235 is enriched to 3.2%. Here there are some components in the reactor. What is called moderator, coolant, and steam regeneration assay. See, moderator. What exactly is moderator is this uranium U235 when it is undergoing fission reaction. To undergo a fission reaction, it needs a neutron, I said. Okay, one atom needs a neutron for it to split. Okay, I will do one thing. Let me just give you a brief of this, then we will go to mechanism of the reaction. Okay, so there are several reactors. PWR is pressurized water reactor. Then it is CANDU. CANDU means Canadian uranium reactor. Okay, then other name given is PHWR. That is pressurized heavy water reactor, which we have in India a lot. Okay, then BWR is called a boiling water reactor. Okay, then it is MAGNOX is a magnesium alloy oxide, mixed oxide reactor, uranium reactor. Then AGR is advanced gas reactor. Then HPGR is high temperature gas reactor. RBMK is a Russian name. Okay. Then FBR is fast breeder reactor. Okay. These all you have to be conversant in future. Okay. Then AHWR is called advanced heavy water reactor. So these are the reactors which already have existed on this planet Earth in different countries. Okay, we have PHWR and we have established the FDR and we have advanced heavy water reactor VHWR also. We have. These two are installed as a test reactors. We are just doing some testing on it. So, but they can produce even power also. So can we go to the next? No, here this is what I was about to tell you. So nuclear fuel materials are there. As I said, uranium is the basic material. Uranium exists. There are some fertile fuels as well as fissile fuels. So fertile fuels are, you may be knowing what is called a fertile fuel. Good. Somebody I heard. Yes, good. So fertile fuels are those which don't give any energy, whatever we do. Okay, like if we burn them, they don't give energy. But whereas fissile fuels, if we make them to undergo a reaction, they give out energy. So that's the difference between fertile and fissile materials. But fertile materials, so then they don't give any energy when we try to do that fission reaction. They are not of any important, correct? But no, these will these take neutrons to transmute into fissile materials. Got it? This fertile material U238 is there. No? U238 will take some neutron to it will get converted to plutonium. Plutonium 239. So plutonium 239 is a fissile material. So these fertile materials can yield fissile materials. That's the reason they are very important for us. Okay. Now here I have just given for you to understand one pellet of, you must have seen that pellets and all very small. So that one pellet of uranium can which the pellet gives out releases equivalent energy like 480 cubic meter of natural gas is burnt. That much of energy only one pellet will give. So this indicates that our fuel requirement is very low compared to other resources like oil or your coal or your gas. 1 ton of coal if you burn, the amount of heat generated is equivalent to one pellet which gives energy. So it is equivalent like this. So our requirement of fuel is very little actually. Okay. Can we go to the next slide? This is what I was about to say. So U235 is a fissile material. Fissile material undergoes a fission reaction. So an incident uranium neutron will bombard a U235. Then U235 and it becomes unstable there. Okay. And you all, I don't have to go into basic atomic science, like why a reactive material is radioactive, and right, you all know about it. So it becomes unstable because of one neutron getting loaded into the nucleus. So immediately it will split because of its instability. Why it splits? It is an indicative reaction. Like we have given there barium and krypton. So barium and krypton are two elements which are byproducts after this fission. It is not that always barium and krypton only will come. No, there are many combinations that we will try to see. So in this reaction, what happens? Free neutrons are also emitted. So these free neutrons will again go in and hit some other uranium atom. So that's how a chain reaction occurs. Okay. So in the meantime, the energy which is released is drawn off from our reactor by the material, the coolant and the primary group coolant and secondary group coolant. Okay. Then similarly we have fusion reaction also. This is one other reaction where fusion can take place. Here it is H2-1. This is called a deuterium. Hydrogen has three isotopes. Okay, one is hydrogen, that is only one proton. Second is deuterium, which has one proton and neutron. There is tritium, which has two protons, two neutrons and one proton. So if we make this two atoms, that is one deuterium and tritium, when they combine, combine in the sense when they are allowed to react between each other, it is very difficult actually. But if it is done, then it releases a lot of energy. A product of this reaction is helium. Okay. When we compare this, of course, I am not given here, but you can just note down the reaction. This one particular atom, when it is fission is occurring in this fission reaction, one fission can give some, let us say, X amount of energy. But in this fusion reaction, one fusion reaction can give 4 times more energy than what we are getting from the fission reaction. So fusion reaction is very, very potential to get higher energy. And this is what we must have read. The reactions which are happening in the sun are nothing but fusion reaction. Hydrogen gets burned continuously and we get like sunlight comes from there. A lot of burning is happening. So we go to next slide. Go to the next slide. So this is the chain reaction, how it happens. One incident in neutron. Okay, but in the reactor, what happens is we put all uranium there. Okay, but this neutron has to be supplied into the reactor to start the reaction. Okay, one neutron is sourced from several elements. There are many sources. Okay, basically in India we use beryllium. There is an alloy. If this beryllium alloy is beryllium alloy is hit with some gamma ray, this beryllium alloy will release one neutron. That neutron will go and hit one uranium atom. That's the first reaction. Okay. Then it will split into two other byproducts, but the energy and the more neutrons will go and hit other uranium atoms. That's how it goes, a chain reaction occurs. Important thing here is we have to control the reaction, because every atom when it is undergoing a fission reaction, it releases enormous heat. What is the amount of heat? I told you it is around 400 MeV. MeV is mega electron volt. So one atom will give 400 MeV. Like that, several atoms are undergoing fission at a unimaginable pace. Okay. So continuously heat is coming out. So that heat we have to draw out. But in not drawing out that much of heat is just not possible to humankind. Okay. So what we do is we try to control the reaction. So not to go at that high pace. So what we do is we put some control rods. Okay. What these control rods do is they absorb the neutrons. These neutrons are generating in the reaction. What is happening actually? This splitting fission is occurring because of neutron. So if we control the availability of neutrons in the reactor, then we are able to control the reaction. Otherwise, it is a big bomb, nuclear bomb. So that should not happen. So we have a control rods mechanism where they are going into the reactor. They try to absorb lot many neutrons there, and they get positioned at some particular level. Okay, so that the amount of neutrons which are generating and the amount of neutrons which are lost into the through the reactor into the atmosphere or surroundings, and the amount of neutrons absorbed by the control rods. If there is a balance, then the reaction is at control. So that particular stage is called criticality. Okay, understood what is called criticality in the sense? Other way around, the reactor is ready, you are able to draw out a consistently the power which is to be generated by a reactor, the designed power, that much is consistently coming out. So that is called a stage where a criticality has occurred in the reactor. Okay, so attaining that criticality is also very tough. No, people, all the scientists work day and night. Okay, they sit before the in the control room and then continuously observe all the parameters, sensors where the neutrons are going high or low or are being balanced or not. So once a criticality is achieved, then the control rods are at that level only. The pumping pressure is maintained. The energy output is also maintained. So getting criticality is very important in a nuclear reactor. So okay, can we go to the next slide? As I said, the reactor does not give only barium and neutron, it gives strontium and xenium, it gives barium and luster, it gives rubidium and cesium, and tellurium and zirconium also. Like this, all these are byproducts in a nuclear fission reaction. So we are only interested with respect to energy. Okay, energy we are drawing off, heat we are drawing off, but these all will spoil the reactor actually. They are producing in the reactor, but these all will not allow the reaction to go forward because these elements will again absorb the neutrons. When they are absorbing the neutrons, what happens? Reactor will again, reaction rate will come down. Number of uranium atoms which are getting undergoing fission will come down. So that what happens, it goes below critical. So it should not happen. So what happens is, as I said, the uranium which is there in the reactor, for example, we have a PSWR in India. PSWR is a natural uranium reactor. I mean, worry you are. PSWR is pressurized heavy water reactor, is a natural uranium reactor. Natural uranium, I said, what is it? It will contain only 0.7% of U-235. So 0.7% of U-235 is allowed to get consumed to the level of 0.3 only. So we are from 0.7 to 0.3. That much of uranium only is allowed to burn in the reactor. Remaining cannot be burned because these all will not allow the reactor to undergo the uranium fission. Got it? You understand? These elements which are formed, they are all high neutron absorbing elements. High neutron absorbing elements. As I said, control rods are also high neutron absorbing elements. So like the control rods materials are cadmium, boron, dysprosium, gadolinium. These kind of materials are used as control rods which have high neutron absorption cross section. So they absorb neutrons instantly. So likewise, these elements also will absorb neutrons, which will when these neutrons are the density in the reactor, neutron density in the reactor is coming down. What happens? Fission reaction will not happen. Got it? So to control the reactor at criticality, we have to compromise with the burning level in the reactor. So only up to 0.3% of uranium 235 levels we have to remove the bundle that uranium from the reactor, and this uranium from the reactor which is removed is called spent fuel. We have already consumed it, so it is spent. So this spent fuel is taken out and a fresh uranium bundle is placed in the reactor. So reactor is a continuous process. Okay, there is no like it is not stopped and refueled. No, it is a continuous fuel where fuel is continuously replenished into the reactor. Can we go to the next slide? Here I have just given only few terms which these are very basic, like at school level or college level, you must have see in these terms. One is criticality. Criticality is what just I have told, the neutron balance. The amount of neutrons generated, amount of neutrons lost, and amount of neutrons consumed. So if this is balanced, then the reactor is said to be at criticality. Okay? The neutron source is, I said that beryllium and antimony mixture is used, and when gamma ray is incident on it, it will emit a neutron. Okay. Then control rods is what I was saying, no? Cadmium, boron, gadolinium, dysprosium, cobalt also is used, hafnium also is used. They are all high neutron absorbers. This I have given that 2550 barns per cadmium. So barn is a unit to express the potential neutron absorption capacity. Okay. So barn is a unit of area. One barn is nothing but 10 to the power of 24, 10 to the power of minus 24 square meters. That is the area unit. It is extremely barn. Okay. Then it is moderator. This is a very important thing, moderator in a reactor. As I said, we have PHWR, that is pressurized heavy water reactor. So in the pressurized heavy water reactor, one we have already seen, uranium is always there in the reactor. So when heat is generated, uranium heat generated or released has to be drawn from the reactor. So for heat to be drawn off, some source should be there. That is nothing but a liquid water, I said. But that liquid water here we are using is heavy water. We call heavy water. Heavy water is deuterium oxide. So like H2O is D2O. So D2O is heavy water. Why specifically D2O is? Just go back to the reactor. Now you see the reactor, uranium is undergoing a fission and it is releasing some neutrons. These neutrons which are released, they are at a very high velocity. It is an explosion. Actually, when during this Deepavali, we firecrackers and all, bombs and all, when that you call hydrogen bomb and all, it releases a lot of energy when it is exploded. You know, when you are around it, you will feel that force of air or gas which is touching us. You know. So the gas pressure, the particles which are coming out from the bomb are at very high velocity. Okay. Here also, when the uranium atom splits, it releases neutrons with that high velocity. But these high velocity neutrons will not bombard the or will not split the uranium atom. Could you understand me? A uranium atom, an incident neutron has to be at a particular velocity only. If it is high, this uranium atom will not split and there is no energy. Okay? Are you able to understand? What is required is a neutron which has a sufficient energy to split. That sufficient energy is to the level of 0.025 electron volt only. Okay, this is a value which may be confusing. I will say rather the velocity of the neutron, the conventional unit which you understand is speed, will be centimeters per second or meters per second, right? In this case, if the neutron which is having a velocity of around 10 to the power of 5 centimeters per second, okay, at that speed it can split the nucleus of a uranium. If it is more than that, it will not split. It will collide like this and go away. It will scatter, but it will not split the uranium atom. Okay. So the neutrons which are generated in the reactor after split, they are their energy level is somewhere around 2 MeV. But what we want is 0.025 EV, not mega, it is electron volt. Generated is 2 MeV, 1 to 2 MeV. So their velocity is somewhere around 10 to the power of minus 10 to the power of 20 centimeters per second, but we want only 10 to the power of 5 centimeters per second neutron only for the fission reaction. So what to do? The neutron which is generated is of no use, correct, in the reactor. So what happens? We have to slow down the velocity of the neutron to that level where this neutron is of some use for our splitting of uranium atom. So this is done by heavy water. Okay, heavy water is filled in the reactor. Okay, this neutron when it is ejected out of the uranium atom, this will go and hit the every nuclei of heavy water, and there is some scattering happens when you throw a ball against the wall. What happens? It will go and then hit it. Its speed reduces. It will fall down there. Correct. Similarly, neutron also will go and hit the nucleus of the heavy water, and then it will slow down. So this is a mechanism. This is called this heavy water is called a moderator. So high energy neutrons are moderated to a level where the neutrons can contribute to fission reaction. So in our nuclear technology, we call these neutrons are thermal neutrons. Got it? These neutrons are called thermal neutrons. Okay, 0.025 eV energy neutrons are called thermal neutrons. So that is about moderator. Now we are using in our PHW heavy water, but elsewhere in other type of reactor they use graphite and ordinary water also, even beryllium also is used. So ordinary water is used in ordinary water has high neutron absorption, whereas heavy water has low neutron absorption. That is the reason we are using heavy water in our pressurized heavy water reactors. And ordinary water is used where neutron economy is really not a worrying factor. So in first type of reactor which I have shown, pressurized water reactor, where in a enriched uranium is used, there ordinary water is used. Then coolants. Coolants is the heavy water is running in our. Can we go back? Further. And then further. One more. Here, this red loop line is heavy water line in our PHW reactor. Okay. This is the primary circuit where the water is drawing off heat from the reactor. Where neutron flux of neutron density is very crucial. That is the reason this is heavy water. But the blue circuit is there. That circuit can be ordinary water, okay, or any other coolant. But here we are using in our India, we are using heavy water there also. That is the secondary of the heavy water in our PHWRs. So why we are using is in case there is a leakage in this circuit, this activity, radioactivity, this all uranium is all radioactive now. So the active water can contaminate that area. So not to contaminate, that also is used as a heavy water. And finally, here after the turbine and all, that water is seawater. That there is a pump there and going over water from the sea. We are drawing water and going into the cooling tower and cooling this steam which is coming from the turbine. Okay. Go further. Again, so that is back. That is what is the coolant. This is the drawing of the heat. Radioactivity is very important factor in nuclear industry, where DAC is derived air contamination. So radioactivity is dangerous actually. You all may be knowing. So alpha, beta, gamma rays must have studied disintegration of radioactivity into alpha, beta, gamma ray. So alpha, beta, alpha can be stopped with anything, even a paper, but beta will penetrate. Okay, and the gamma will also go. So beta can be stopped with some metal foil and all, but the gamma cannot be stopped with metal. It will penetrate. Only lead can stop the gamma. High intensity gamma and beta will damage our body cells. So that is the reason this area where reactor is there, people are not allowed to go. It is all done remotely. There is some automation and all. So the entire reactor is closed. People cannot go inside. The reactor you must have read that. No? It is a containment. Reactor containment is what written there. So containment is where in which reactor is there. Steam generator also is there. That is all closed. How it is closed is there will be a concrete all around. Concrete walls will be there, and concrete wall is not just like not like this wall. Almost 1 meter to 1.5 meter thick wall will be there. Okay, concrete. Then after that there is a metal wall, that is a steel wall. Then there is after that there is a lead wall also. So these three layers will protect the reactor, protect the environment also from not getting any contamination leaked from the reactor into the area. So that is the reason radioactivity is very important to stop in the reactor itself. Then what types of fuels? There are many types of fuels. Okay, U-235 is what we are using in India. Okay. Then PuO2 is plutonium oxide fuel, which we are using in FBR, fast breeder reactor. And MOX fuel also is a fast breeder reactor. Uranium metal is used in only test reactors. Then thorium is used in ASWR. Okay. So these are what fuels. Then reactor containment, I told you already how it is done, that I have given. Can you put the next slide? Now in India, as I said, our type of reactors which we have established and continuously using are PHWR, pressurized heavy water reactors. Okay, in which natural uranium is used as fuel. Okay, so we have a in 1950s Dr. Homi Baba, who is the founder of our atomic energy department in India, has envisaged a 3-stage program. So how no other country has envisaged this, only India has envisaged. We are very proud to say. So how it has come is uranium-235 undergoes fission. Okay, it gives energy. We are drawing, we are converting to electricity, and we are using it. But what happens next is, in that, as I said, 0.7% of uranium-235 is only fissile. Remaining is U-238. Right? For example, 100 kg is there, 7 kg is U-235, and remaining 93 kg is U-238, which is of no use. It is like a muddy. Okay? But this, as I said, it is a fertile material which absorbs a neutron, gets converted to plutonium. Okay? This is called transmutation, nuclear transmutation. So here you see uranium-238 taking a neutron, emitting some gamma and all, it will convert to plutonium-239. Okay? This is a nuclear reaction. It is not a fission reaction which will give energy. So this is called transmutation. So plutonium-239 again is a fissile. You must have read that in that fissile materials. No? So plutonium-239 is fissile. What happens from spent fuel after burning? I said no, from 0.7 it will come to 0.3. 0.3 material is removed out. Okay, this is again processed, broken open. All this uranium is removed. Again we process it as we have processed the uranium. So in this, what happens? You have a gold here. That gold is nothing but plutonium. Okay, plutonium is extracted. Okay, separately, and then again made a fuel. That is plutonium oxide. This plutonium oxide will not be used in our natural reactor, that PHWR. They have to be used in a different type of reactor, that is called fast breeder reactor. Got it? Fast breeder reactor. Why it is called fast reactor is the PSWR which I said is a slow reactor and FBR is a fast reactor. So the fuel which is the plutonium is a material which can absorb or take a positive neutron for splitting. Whereas in case of natural reactor, that PSWR, what I said, uranium can take a slow neutron. Could you remember or no? Uranium-235 will take a slow neutron. The fast neutron is slowed down using moderator to a level or thermal levels, that is 0.025 and electron volt, and that energy neutron only is splitting U-235. But plutonium will not get split with slow neutrons. It will split with fast neutrons only. Fast neutrons high energy, that is 1 to 2 MeV electron neutron. So this cannot be used in the reactor which we have established, that is PSWR. So this will this material is used in a other reactor which I said fast breeder reactor. So fast breeder reactor, plutonium, uranium also is put, along with that some thorium also is put in the reactor. Okay. So what happens is the plutonium will burn. Okay. Plutonium will split. It will give energy. We are drawing out. But the uranium which is there made, U-238, it will take neutrons, fast neutrons, and convert to plutonium. So what happens in the reactor, in this fast FBR, the plutonium is consuming to release energy, but uranium-238 is converting by transmutation to plutonium again. So amount of plutonium lost or split and then consumed for energy, that is some quantity. But the uranium which is uranium-238 which is converting plutonium, so some plutonium is generated in the reactor. We want only plutonium, but uranium is generating plutonium also. So the amount of plutonium consumed and amount of plutonium which is generated, if you check these two in the reactor, the plutonium generated is more than consumed. So reactor will not stop it. Okay. So this is the reason this reactor is called a breeder reactor. Breeder means it is breeding. If you know mosquito breeding, like that, here our reactor breeds fuel within the reactor. So how it is happening? Because we are using plutonium as a fissile material. We are putting along with that some uranium-238, which is a fertile material, getting converted to plutonium, which is a fissile material, and that is contributing to energy output. So when it is checked, the amount of plutonium which is consumed and the amount of plutonium which is generated in the reactor, the generation is more. That's the reason it is called a breeder reactor. Along with this, in the second reactor, I told some thorium also is put. Okay. Again, thorium is a what type of fuel? Yeah, fertile fuel. Yeah. So it is fertile fuel. Fertile fuel, what happens? It will absorb some neutron and then it will get converted to U-233. Okay, U-233 again is a fissile material. This fissile material again will not burn in this reactor FBR, because that is a material which is suitable for slow reactor. So like that, it can come back to PSWR. Okay, it can come back to PSWR where slow neutrons can be incidented onto the U-233, which will split and then give. So we have first stage reactor as PSWR, where uranium-235 is used to generate electricity. Okay, then in this the U-238 which is there, which is fertile material, gets converted to plutonium. This plutonium is extracted from the spent fuel and used in second stage reactor, that is FBR. FBR is a fast breeder reactor. So plutonium burnt in this fast breeder reactor, we get energy. But in this, that uranium-238 again produces more plutonium, so it is called plutonium. Along with that, they are putting some thorium also. So thorium will absorb these neutrons, gets converted to a fissile material, that is U-233. I think I'm confusing you all 233, 238, 230 right now, but this is science. Okay, so to uranium from second stage, the spent fuel is removed. From there, we extract that uranium 233 exclusively, and that we use in a third stage reactor, not in PHWR, because U233 is having high energy potential. When you compare one fission reaction will give more energy than what PHWR. So it is a special reactor which is put in a third stage. So that is called AHWR that we have mentioned at the bottom, advanced heavy water reactor. That is there also moderator is required, which will slow down the neutrons in the reaction during reaction, and this slowed down neutrons will split U233. But here again we put more of thorium in it along with U233. Thorium. So what happens is thorium again is a volatile material which will absorb neutrons. So the neutrons which are generated in the third stage, the neutrons will are absorbed by thorium. Thorium gets converted to U233. What is consumed is U233 in the reactor. Okay. In HW, U233 is consumed, right? Along with that, we have put some thorium. So thorium is converting after absorption neutron into U233 again. So this reactor is will be working endlessly. You don't have to put material in it. The thorium which is there, as long as thorium is consumed, so long we can run the reactor for years together. Even if you say for about 100 years, it can run without any fuel. If you size the reactor for 100 years, the reactor will run 100 years without any fuel. But in PHWR, the first stage reactor, we have to fuel the reactor regularly, as the percentage of U235 from 0.7 to 0.3 is coming in. So we have to remove that from it. Okay. In case of FPR, the second stage reactor, as the plutonium is getting breeded, but along with that, there are, as I told you, byproducts are there which will reduce the neutron economy. But in the third stage reactor, this is not there. So we have established in India, only India has established the third stage reactor AHWR as a test reactor, and one of its kind in world, and it is running. The name of the reactor is called Kamini, and the reactor is able to generate around 30 megawatt energy. And the last 30 years it is in India. No other country has this reactor. So it is we have to be proud being Indians, but we have that good technology and Dr. Homi Baba, who has envisioned them last 70 years back. Subsequently, we have realized it and then established a test reactor. But why we have not gone for a full-scale reactor? There is a question. But for that we want U233. So U233 we don't have sufficient U233. To get U233, we should have phosphate reactor. We are coming back again. So phosphate reactor we don't have. We have established one phosphate reactor as a test reactor. That also is running last 30 years in India. Okay, only 3 countries in the world have this phosphate reactor. One of them is India, but it's a test reactor only. But phosphate reactor, why we have not established many in India is we don't have sufficient plutonium. Plutonium has to come from first stage reactor, that is PHWR. Could you understand? Okay? So, can you go to the next? This is the last equation which I have shown. This is the transportation equation. Thorium is converting to U233. You see, this is happening in the which stage? Second stage. We are putting thorium as well as the third stage also. Thorium we are putting in the second stage as well as in the third stage, which will convert to U233. U233 gets consumed in AHW. Can we go forward? So this is about the 3-stage program. I think I've taken a lot of time. I close it, sir. 5 minutes. There is a third stage, the 3-stage reaction, 3-stage nuclear power program. So first is PSWR, second is FBR, third is ASWR. So PSWR is here we are using natural uranium and it is generating electricity and we got depleted uranium. Okay, DEPU is called depleted uranium or spent fuel. Okay, that spent fuel is removed and then processed. Okay, we are extracting from that, we are extracting plutonium. Plutonium goes into the second stage, that is FPR is the second stage reactor. Plutonium goes into the PU fueled fast reactors. Okay, fast reactor. From there, U-233 is coming because we have put the thorium from the top. Okay, so thorium gets converted to U-233. U-233 goes to the third stage reactor, that is ASWR, and ASWR. Along with that, we put thorium also. Thorium, as I have shown you, last reaction of nuclear reaction, where it is converted to U-233. So in that last reactor, ASWR, uranium-233 is fuel. Along with that, thorium we are putting, it will get converted to U-233. So it is a closed loop. U-233 is consumed and U-233 is generated in that reactor. So that reactor will run forever. So that is the idea. So this is our three-stage program. India has envisaged it, and to get realized ASWR, it may take another 100 years minimum. So in this 100 years, we will be able to produce more 233 to make those reactors work. So we have this is a time. Sufficient time is required for generating that U-233. This is about the three-stage program. Okay, can we go to the next slide? Okay, these are the future technologies. Now SMR. SMR, you must have heard in the news, recent news. What is that? Yes? It is there in the news, recent news. Small and medium scale reactors. One nuclear reactor in India now, PSWR, is spreading around 200 acres of land. Okay, but this SMR can be put on a small truck and brought to your company or your campus also. So over a period of time, scientists have worked on it, and a nuclear reactor they have made so small that it can be transported, it is portable, it can be used anywhere. So in the world now, in the last say around 10 years, around 130 such small reactors, small SMRs have been made and then are on use at required locations where, you know, for example, a steel manufacturing company is there where a lot of energy is required. So they get the power from the grid, there is a substation and all. But you know, if this reactor comes there, they can install, okay, somewhere in a close room, and from there they can draw the power. They don't have to depend on the grid and the power supply. So that is the advantage of a SMR. So India also, we have to be proud again. India also has developed. We have around 5 small and medium SMRs in India, and you must have read in the news, but we don't generally focus on it, try to understand. We have nuclear submarine. Have you heard? We have nuclear submarine in India, and nuclear submarine is fueled with the power generated from a nuclear reactor. It is floating. It is installed in it is a small, something like a 2 meter by 2 meter by 2 meter. That small area, a reactor is there. This is installed in a submarine, and that is running. Okay, like that we have around 4 are running. 5th is getting manufactured in India. This is all indigenous technology. We are not dependent on any other country. Our engineers, our scientists have developed it, and we are about to make more and more. As we now, you must have heard about this news. Lot of news is there about data centers and all. Amazon data center is in Hyderabad. You know what is the power consumption rate? Does anybody know? You don't know. Okay. So such kind of establishments require large amount of power. These powers can be yeah, from this source. So SMRs will come to the need of this their need. Okay, so in future we may get many such SMRs which can provide electrical supply to various types of installations. The software company is there, and any other factory is there. They don't have to wait, or they don't have to. These SMRs will give a consistent supply. There is no power breakdown. There is no short supply and all. It will give continuous power. Okay? That is the advantage of SMR. Then next is Gen 4 concepts. They are next generation. I said a three-stage reaction. No? The three-stage nuclear program is there. These are about the fourth stage. They are MSR. MSR also you must have heard. Molten salt reactor. Have you heard anywhere? Now even that is there in the news nowadays. Have you heard? Molten salt reactor. That is a thorium reactor. Okay. Then SFR is again fast reactor only. HTGR is high temperature gas reactor. LFR is also liquid fuel reactor. So the advantages I have written there. Advanced fuels, many HALEU is the advanced fuel is what the world now speaking about. Uranium alloy enriched uranium also is used to the extent of around 93%. So anything above 20% is a bomb grade. Okay. But 93% is a bomb only. But that is used as a fuel in reactors, which is very difficult to handle. But still, man is progressing to developing the technologies to use that kind of uranium also for reactors to develop. And the other one is fusion. You all must be knowing a lot of last 10, 15 years this fusion reaction is there in use. Have you heard about this ITR, CERN, CBR? Yes, somebody said yes. Heard? No, you don't read newspapers? ITR is International Thermonuclear Reactor. So, where fusion reaction is proposed and then research is going on. So, fusion reaction, as I said, fission reaction will give some X amount of energy. Fusion can give 4x of energy. So which is happening in sun. Okay. So here same deuterium and tritium are used. Okay. And are used for generation of power. So this deuterium and tritium both are hydrogen isotopes. Both are in liquid or gas state. But this the nuclear don't come together very easily. So they need a high energy for them to come closer and then react to each other. So that is the reason we are failing to supply that much of energy for the reaction to happen. And then to take out, to draw out the heat, energy released also is a big task. We cannot draw heat from the sun. We cannot go to the sun at all. When sun is there before us, the man cannot survive. Correct? Man cannot survive. There is a sun adjacent to us. So that is a difficulty. So ITR is a facility where man is struggling to make this possible and then draw a consistent supply of power. So we are at that stage now. So very sure, we are very fastly progressing to it. And we are sure that we will establish the technology for that also. This is about the future technology. What is the next one? Okay, same. I think take this one again. Thank you. I have been talking to you all people, but I thought it will enlighten you with respect to nuclear power in India and all, how we are progressing and all, and what is the importance of power for development of our country and all. So with that idea I come, but I hope I have not bored you all. Thank you for patient listening. Thank you.
you so much, sir, with your valuable words, sir. The stage has enlightened today. On behalf of everyone present here, I would like to express our sincere gratitude to you in delivering such an insightful and inspiring session today. Your valuable time, deep knowledge, practical insights have truly enriched us. The way you explain the topics of uranium production, types of nuclear reactors, nuclear transmutations, and future technologies, third stage reactor dominate, which such clarity and real life examples made it encouraging and easy to understand. Your presence and contribution have added a great value to this seminar, and we are truly thankful for your efforts and dedication, sir. Once again, I thank you for sharing your experience with us. Please give applause to our guests, sir. We hope to have the privilege of learning from you again in future, sir. Thank you so much, sir. Now is the time to honor our guest speaker, K. Nageshwar Rao.
No. Okay.
I request our respected principal, sir, to facilitate the speaker, sir. I request the respected principal, sir, to facilitate our respected guest, K. Nageshwar Rao Garu, NFC, Executive Officer, Hyderabad. I request faculty members to join the gallery for with the speaker. I request faculty members to please join the stage. Now it's the time to declare the Do anyone have questionnaires from the end of seminar? So I would like to talk about the seminar questionnaires. Do anyone have any questionnaires?